All right, in this video we're going to look at some more limits where x is approaching infinity or negative infinity, and we want to find the answer to this limit problem also, but also make note of some kind of compare and contrast between the examples that we're looking at. All right, so for this first one, one thing that you might notice is that the numerator and denominator both involve variables. So some of the other problems we looked at, we only had variables in either the numerator or denominator, one place in the function. So when x grows large, the denominator is going to go large, and the numerator will grow large in size. We'll have a negative, and then add the constant 1 to that. So both the numerator and denominator grow infinitely large this time. So sometimes students will talk about this as being a limit where I have infinity, or actually on the numerator, negative infinity over infinity, and think that they can draw a conclusion about what that limit is based on that. That's actually called an indeterminate form. Our textbook doesn't talk about it that way right now. It does later in some later chapters, but what that means is that you can't determine what the limit is from that form. You have to do some additional work to determine what the limit is. So for this particular problem, I can do a little bit of algebra to rewrite the function, and then it should be pretty straightforward for this one to figure out what this limit is. So this one is nice. We'll look at some that are not quite the same way, but this one's nice because the denominator is just one term. So if you think about how you add fractions and then unadd fractions, you can rewrite this one as the limit as x approaches infinity, and then I can split this up so that I have a denominator of x under both of these terms in the numerator. Most of the time in algebra, you did that step the other way, where you had two fractions with a common denominator, you combine them into a single fraction with that common denominator. But here we've kind of split that up. And the reason that that's really helpful is that in the second fraction in particular, that just reduces. So I can rewrite that as the limit as x approaches infinity of 1 over x minus x squared. All right, now I can think about each of these. Now I've really got two separate terms here, and I have x only once in each of those terms. All right, so as x grows without bound, as x gets larger and larger and larger, thinking about the value of this part of that expression. So x is getting larger and larger and larger, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, keep going, keep going. The value of this fraction here is approaching 0. It will be slightly larger than 0. It will be positive, so it's approaching 0 from the positive side. And then thinking about this term here, as x grows larger and larger and larger without bound, and then I square it, that's going to get even larger and larger and larger. So this part here will be approaching positive infinity. So when I look at the limit of the overall expression here, I've got something getting close to 0 minus something that's growing larger and larger and larger without bound. So we might write 0 minus infinity, and that limit then is negative infinity. This is a step that you may or may not write, but there's the answer for that limit problem. Okay, so just to contrast with that, I'm going to look at another limit problem where we can't quite do the same algebra, but we can use some logic in thinking about function behavior. Okay, so for this one, again, have a fraction with some variables in it. This one is a little easier in some sense because I have x only one place in the expression. So if I can think about what that part of the function's doing, then maybe I can think about the overall limit of the function. So this is one we actually looked at in a previous video. As x approaches infinity, what happens to the outputs of the e to the negative x function? I graphed the e to the negative x function, and we talked about horizontal asymptote at 0. So the values of this part of that expression are approaching 0. They will always be positive. So I put a little plus there to indicate 0, but above 0. But this part is approaching 0. The rest of it just stays 1 and 7, and so I can think about the limit of this overall function as 1 over 7 minus 0, or 1/7. And again, this step right before the answer, you may or may not actually write that, but that's how you would think about getting to that answer. If you needed some justification, you could write that. You could write something like this as well, or maybe even a sentence explaining what's going on with that e to the negative x function. All right, let's look at this same function actually, but let's look at what happens as x approaches negative infinity. Okay, so same function, but this time I'm going to let x approach negative infinity. And so we looked at just the e to the negative x function in a previous video. As x approaches negative infinity, we talked about it graphically and numerically. So as x approaches negative infinity, because we've got negative inputs and a negative in the exponent here, that would make that exponent positive. So this part here, I'll end up with e to a very large in size positive number, because the negative times the negative. So this part that I've circled here will approach positive infinity. And then on the denominator here, I'll have 1 over 7 minus infinity. So that denominator will be approaching negative infinity. And so then thinking about the value of this expression as that denominator approaches negative infinity because 7 minus a large in size number, the value of this fraction will be approaching 0, but on the negative side of 0. So I can put 0 here. Probably that would be a fine way to put that. If you really wanted to denote which side of 0 that's approaching, you could put a minus up there to indicate on the negative side of 0. Standard notation in our textbook often uses the pluses and the minus to indicate what's happening on inputs of functions. Does not always use that on the output of the function, the answer to a limit problem. So this part here where I put the minus, you could put that there, or not necessarily. It might be important to you to know which side of 0 those outputs would be on. All right, let's look at one other just modification of this same problem here. I'm going to put an e to the x function on the numerator and just do a little bit. Let me make this we'll just make it a +1. All right, so another similar kind of problem. I've got e to the x's on both the numerator and the denominator. And e to the x instead of e to the negative x in this case. All right, so I want to think about all these little pieces of the function and what they're each doing. So as x grows large, this e to the x grows large and approaches infinity. As x grows large, this part also grows large and approaches infinity. And so when I take this numerator approaching infinity, I have the denominator 7 times a large in size number plus 1. That'll be very large in size. So the denominator is also approaching infinity. So just like this first example that we started with up here at the beginning, where I said we have a numerator and denominator both getting large in size without bound, that's actually an indeterminate form. So that does not necessarily mean that the limit is 1. Infinity over infinity is not necessarily 1. It means you have to do more work to figure out what that limit is. So I'm going to do something on this one that our textbook actually does not do, at this point anyway. They talk about it later in the textbook, much later in the textbook. But I'm going to talk a little bit about this function and what happens when x is large. And I used this word in the last video where I talked about dominant terms. So in a polynomial, a dominant term would be the largest degree term. But in this expression here, it's not really a polynomial. I've got this exponential function here. But on the denominator, I have 2 terms. The +1 has hardly any impact on the size of that denominator, especially when x is large. This term here is the dominant term. So I'm going to just focus on the dominant terms here. Dominant terms. And not that this function I'm going to write down is equal to the original function. Right, so what I've done here is I've ignored the +1. This function that I have here is not the same as this function that I have here, but their limits will be the same. They behave the same when x grows infinitely large. And the nice thing about this one, where I ignored that term that has almost no effect on the denominator, is that this function actually just reduces. So e to the x over 7 e to the x actually just reduces to just 1/7. Right, so between the first step and the second step here, I actually used an idea about limits. These two functions are not the same. But between my second step and my third step, these two functions are the same. E to the x over 7 e to the x and 1/7 are the same function. That really just reduces algebraically. All right, and now it's pretty easy to think about this. As x grows large without bound, 1/7 stays 1/7. So this limit is 1/7. And I want to just contrast that problem with the first one we looked at. So both the first one and the last one had functions where both the numerator and the denominator grew large in size, but notice the difference in the kind of answers we got to both of those problems. So those are intended to illustrate that you can't just focus on numerator and denominator. Sometimes you can if you have a simple function, like these two middle examples had only x in one place. But you're going to have to do some algebra or some thinking about the function behavior to rewrite that in a form where you can more easily think about what the limit of that function is.